Greetings and welcome, friends. Mr. Waddy here. Me and my friends in real life, just going over some math problems from last night's homework on page 160. We invite you to join us. This is going to be wonderful. So hopefully they've got some questions along the way for clarification if my explanation is not sufficient. So here we go. It says graph the function. Compare the graph to the graph of f of x equals the absolute value of x. Then it said describe the domain and the range. So let's first of all graph f of x equals the absolute value of x. Now that's kind of like the line y equals x. It's got a slope of 1, a y-intercept of 0. And if I was to draw that, it'd be like this, just up 1 over 1, up 1 over 1, etc. Right? Let's see. Ooh, look at, I think that line, oh yeah, it's a nice 45-degree angle up there. Notice that? Lovely. That's exactly what I need. And so for an absolute value graph, it kind of looks like this, except then you got to remember one thing. Absolute value can't be negative. This doesn't exist down here, right? Because absolute value will take these negative points and make them positive. So it's going to have a V-shaped graph. Yeah, isn't that lovely? There we go. So absolute value will have a V-shaped graph. We call this the vertex, the bottom of the V there, the point where it changes direction. So if I want to graph d of x, notice that it's the absolute value of x, so this will be the parent function, minus 4. And subtracting 4 on the outside of the absolute value will affect in a vertical, give it a vertical shift down 4 units, down 4. So my new vertex is now going to be a 1, 2, 3, 4 down here. And it ain't just going to be the vertex, it's going to be every other point. So this point is now 4 down, and this point is 4 down, and this point is 4 down. As well as like this point, guess what? It's 4 down. 4 down. Yeah, so all of those are now 4 down, and just shifts the entire thing like so. If you wanted, you could, make a table of values, but really, if we can recognize patterns and make our graphs more efficiently by recognizing patterns and trends, that is always going to be better than doing a table of values for our graphs. Just so you can see the way these vertical shifts work, I've got my geometer sketch pad open. And if I have this plus k on the outside of the absolute value, if I shift this and I add a positive number, it shifts the graph up. If I have a negative number, it shifts the graph down, and it does a vertical shift up and down like so. Lovely, lovely. Actually, yeah, we can even make our graph, because it was what, minus 4. There we go. There's our graph. Lovely. You see the parent function as this dotted line, dashed line even, if you will. And like that. Now the next problem we're gonna do is gonna be a horizontal shift, where it can go left to right. But what's weird about all horizontal transformations is they behave in the opposite way that you would expect. Yeah, they don't quite behave the way you would think they would. Oh, domain and range. Oh, you almost got me there. Problem. Here we go. Domain is the set of, the set of all x such that, now in terms of this orange function, what x values work? Well, I can plug in negative numbers all the way to infinity. I can plug in 0, and I can plug in positive numbers all the way to infinity. So the domain is just the set of all x such that, like x, it's just anything. You could say all real nombres, right, is the domain. Now, if I want to talk about the range for this, notice the range. Do I have, I don't have values on that graph for this whole space down here, all the way to negative infinity. It just doesn't have any points that have y values that are less than negative 4. But if I was to smush the orange graph, right, into the y-axis here, the points that it would have been everything from this number up. Okay, and it does go, in fact, up for it. Man, that's the ugliest coloring I've ever done. And it would go up forever. So the way I would describe that is the set of all y such that y is greater than or equal to -4. Right? You guys believe it? I hope so. I hope so. So there's our absolute value graph. So here we go. So how does this one relate? What did I just do? Oh, I just jumped down to 11. And that was crazy. We're going to take this all the way to 11. Don't you worry. There we go. We'll start with 7, though, for the middle problem. So let's see. For the regular f of x equals abs x, right? We're going to have regular absolute value, up 1 over 1, up 1 over 1, up 1. Have the parent function? Oh, the grid? Yeah, I found this one online. Yeah. Oh, you think I should print some out? Yeah, I could print some out for you guys. That's yeah. So yeah, I could print some out. That's a good idea. I can make that happen. Add it to my list. Graphs. There we go. Take a note. I shall remember. So let's see. So that's my parent function. Now I'm adding 1 to the inputs. The inputs. It's on the inside of the absolute value. Okay. So adding 1 is going to change the x values. It's going to change the graph horizontally because that's our horizontal axis. And it's going to be a horizontal shift. All right. But the thing is, even though I'm adding 1, I would expect it to move to the right. But oh no, it done juked me like Madden 2017. It's a shift to the left. Left 1. So the trick with the h is that when you are adding a number, it's moving to the left when it's added on the inside to the x. And if you're subtracting a number, it's in the opposite direction. It would be moving to the right. So don't be fooled, friends. So shift to the left 1. So this point is over 1. This point is over 1. And this point is over 1. This point is over 1. All the points are over 1. All the hippos go berserk. And we would have horizontal shift like so. And then draw this guy right over here. And so it's similar to the parent function. Horizontal shift, though, is all that happened. Now, as far as the domain, did that change the domain for x? No, it still goes all the way to -infinity, right? So all of those values will work, and it includes 0 still, and it goes all the way to +infinity. So yeah, it's just the set of all x, like such that x is anything, right? All real numbers. And how about the range? Now the range didn't change from the parent function, but do you guys know what the range was to begin with? What do you guys think? What possible outputs did this orange absolute value graph have? Does it ever have +4 as an output? Yeah, it actually has it twice. It has it over there and over here. Yeah. Does it ever have 2 as an output? Yep, right there and right there. Does it ever have 0 as an output? Yep, right over here. Does it ever have -1 as an output? No, there's no orange anywhere for all of this space. No naranjas, mis amigos. So the way I would describe this is that the y values, the range, the possible outputs are everything from bigger than 0, bigger than or equal to 0. Right? So there we go. And aha! Now multiplying the outside of the graph by a number outside of the absolute value is going to be a vertical stretch. So vertical stretch. If I multiply by a number bigger than 1, it stretches it up. If I multiply by a number that's less than 1, it smooshes it down. And if I multiply by a negative number, it stretches or smooshes and then flips it. Yeah. What? Yeah, so this one's going to be flipped and stretched is what's going to happen to this one. So you guys know what the parent function looks like. You guys are expert absolute valuers. All right, there we go. There's the original parent function. This one has been stretched by a factor of 5. Let's do this in 2 moves. 1, vert stretch by a factor of 5. Okay, so that means 0. What's 0 multiplied by 5? Still 0. Let's see, here it had an output of 1 multiplied by 5. That is 5. And let's see, 2 multiplied by 5 is 10, all the way up there. And then I can mirror these over the y-axis, or over the line the vertical line that passes through the vertex. And so my new function after a vertical stretch would look like this. There we go. All right, but it wasn't just a vertical stretch, it was also a flip, reflect over which axis? Man, that's an ugly, over the x-axis. Okay, so if I want to flip that, I flip 0 over the x-axis. Well, that happens to land at 0. I flip 5 over the x-axis. Now that's going to be at -5, as well as for this one. I flip -10 over the x-axis, and now it's going to be at -10. And the same for this one. And it just flips it. Flip it. Hey, look at this. I can actually... Oh, not quite. Huh. Well, my points didn't line up quite right, but that's fine. I'm not the best at drawing points, I guess. And let's see, something like that, and that'll do. That'll do, pig. There we go. So there's my upside down absolute value graph. Okay, but friends, we ain't done yet. We are on the last problem, though. 12 minutes in. Okay, domain. This one is, I'll just write all real numbers. Even though this has been vertically stretched, it will still have all of the negatives and all of the positives and all of the 1, 0. Okay, so domain is everything. All right, how about range, though? This one's an interesting range. For the blue graph, it includes 0. And it includes all of the negative outputs, but it doesn't have any positive ones. So I'll describe that as the set of all y such that y is less than or equal to 0. Right? It was all non-positive numbers. All right, thanks for watching, Internet friends. Have a great day.